Hello and welcome back. A close friend to our permutation work is the combination. So this is looking at, okay, well, what happens if the order no longer matters to us? So first up, we're going to do just a quick little warm-up problem related to our 11-7 work. How many ways can we arrange 3 objects if the order matters? So see if you can scribble that out real quick and figure out how many ways we can arrange these 3 objects. Well, hopefully you remember from your 11-7 work that this would be just 3 factorial, 3 times 2 times 1. So 6 ways. There are 6 different orders that we can line up 3 objects. So now let's go back to having a class of, say, 24. So now we're going to have this 24 student class. This time we will select 3. And they're going to be our class reps. Each class rep gets an equal voice. Not different jobs, order doesn't matter. So if the order did matter to us, then we would use the n factorial over n minus k factorial. I'm going to leave a little space in between there. But remember that each of these groups of 3 that we're choosing can be arranged in 6 different ways. So the permutation is overcounting by a factor of 6. So we would just divide also then by 3 factorial. This is the combination. So this is really the only new part. We have n choose k. N factorial over n minus k factorial that you saw back in your permutation days. And then we divide by the n factorial ways you could arrange each group. I'm sorry, k. My apologies there. K. The k ways that we could arrange each group of the 3 students or 5 students or however many in our little subset. How many ways can each of the groups be rearranged? And since the order no longer matters, we divide by that number. So for this one, and I'll also show you some other commonly used notation. In parentheses, no fraction bar. This is the same as the C notation, 24 choose 3. So 24 factorial over 21 factorial, 3 factorial. I'll expand it out until I hit the bigger of the 2 numbers. So 21 factorial cancels. 3 by 2 by 1 is 6. And 6 is a factor of 24. I can knock that guy down to a 4. And then it's just plug and chug on a calculator there. So we've got, on that one, 4 by 23 by 22. So 2024. ways that we would be able to select 3 reps. Another place that we would see this in the math tax world, the gambling world, dealing cards. The order that you receive cards is not important in most card games. So how many 5-card hands can we make out of a standard deck of cards? Standard deck of cards has 52 unique objects. The order doesn't matter to us. We're just choosing any 5 of those cards. So 52 factorial over 52 minus 5, close it up, factorial, and divide by the 5 factorial ways we can rearrange 5 cards in our hand. So 52 factorial over 47 factorial times 5 factorial, and expand it out. So 52 by 51 by 50 by 49 by 48. And that 47 factorial is now going to cancel with the 47 factorial down here. And 5 by 4 by 3 by 2 by 1. Okay. So let's see. 5 by 2 is 10. 50 over 10 is a 5. Let's see. 4 by 3 is 12. 48 divided by 12 is 4. That's all the canceling we can do, and then we just multiply what's left. So 52 by 51 by 5 by 49 by 4. So 52, choose 5. 2,598,960 possible 5-card hands. One more kind of common application in the math tax world still. The Illinois math tax has 52 numbers, and I'm told that they select 6 in any order. So the order doesn't matter. So we want to know how many ways can a winning number be selected. So this, as different as it sounds from some of the other problems, this is another combination problem because they said key part here, any order. The order doesn't matter. This is a combination. So 52, choose 6. Again, remember, you'll sometimes in books see it written that way as well. No fraction bar. This is not a fraction. So 52 factorial over 52 minus 6 in parentheses factorial, 6 factorial. So 52 factorial divided by 46 factorial, 6 factorial. So 52, choose 6. And we'll expand it out. 52 by 51 by 50, 49, 48, 47, 46 factorial. 46 factorial will cancel. And then 6 by 5 by 4 by 3 by 2 by 1. And then we just cancel where we can. So let's see. So 5 by 2 is 10. 50 divided by 10 is 5. 6 by 4 is 24. 48 divided by 24 is 2. And let's see. 3, 51. 3 will go into 51 17 times. So 52 by 17 by 5 by 49 by 2 by 47. So 52, choose 6. 20,358,520 possible winning numbers. So quite a huge selection there. Quite a big list of possible winning ticket numbers there. 20 million and change. Okay, so in this was 11-8, 9 through 51 on the odds. And again, this is really just kind of building off of our work on permutations. The only difference is, since the order no longer matters, we're also dividing by the k factorial ways you can arrange the k objects. Otherwise, our permutation and combination work looks very, very similar, and the problems will sound similar. So just try to be mindful of that. Which ones does it sound like the order is not important? Which ones does it sound like the order is important? If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.